Okay, so we'll speak today about the Bayesian inference approach, which is in the context of talking about generative models. Previously, we talked about generative models. Previously, we talked about generative models, and we optimized parameters to get the best model out of a family of models. Okay? So the parameter we optimized was just a parameter we're trying to find the best one for a given machine learning task. Now the biggest difference when you switch to Bayesian inference is that everything becomes probabilities. So that this parameter becomes also a probability. We treat it as a random variable or a density, basically. Okay, so that's the biggest difference. And once you do that, immediately you get confused because what's the meaning of this? So one very common interpretation is that it represents our belief about the parameter. Okay? So for instance, if the parameter could take values between 0 and 1, so we'll have a density on what the value is. Maybe it's a clinical trial, and we think that most probably the drug is good, so we'll have some belief system about the parameter. That's basically the way to think about it. To give you another example of this type of thinking, if you think about incomplete games of incomplete information, so I'm playing against an adversary, and I'm not certain if the adversary wants to make peace or doesn't want to make peace. So that's my trial. I'm either in a game that my adversary wants to make peace, and the probability for that, according to my belief, is 1/3, or I'm in a game that my adversary doesn't want to make peace, and the probability for that is 2/3, based on my belief, based on previous knowledge and so on. Okay? So that's the philosophy. Once you do that, everything becomes probabilities. You don't have a maximization problem anymore. You just have you are in the context of generative models, and you're trying to estimate some probability under some statistical assumptions. So let me explain that in more details. Okay? So assume we have sample, okay, and we get another point. As this sample is coming from some random variable, and now we get another point, and we want to estimate what's the probability of getting that point given the sum. Okay? If we're able to do this based on the Bayes rule, we can do classification, right?
Yes.
So we're done from that perspective. So that's what we want to do. Okay? Now, what I've introduced now is that I have this density over the parameter, right? So I can think about this as a sum, or whenever I write a sum, maybe later I'll change it into an integral. Okay, depending on the specific of the probabilities of this given given S, given the sample. Okay, so I'm going over all the values, all the values and looking at the joint distribution because now this is a random variable. Now, one difference between our statistical assumption previously and the one that we have when we switch to Bayesian inference is that the independence of the sampling that we previously had is now conditioned on the parameter. Okay? So, and you'll see that in a minute. So let's expand this. So expanding this, I get according to the rules of probabilities, I get that I got the parameter given the sample, and then given the sample and the parameter, I have this value that I want to estimate. Okay? Now, because of the independence, I can basically drop this. This is where the independence comes in. Okay? Because it's conditioned on the parameter. So I have a simpler representation. And now I want to express that based on the information that I have. Okay, so I'll use the base rule. So I need some more space here. So I have base rule tells me that this is basically this as well as this. So given the parameter, I get the sample, or given the sample, I get the parameter. Okay? And so I get that the thing here, that given the sample, the parameter is equal to this. Right? And I can take this and insert it over here. Okay? And this is not dependent on the parameter, so it goes outside. So I'm left with the following thing. Basically, like this, and inserting it here, I get this. Right? So now what you have here is a representation, and giving some assumptions on the probabilities, you can further calculate it. Note that there's another step here that we can make at this abstraction level without making yet any assumption about the densities or the distribution, which has to do with the independence. So given this, the parameter, this is going to be all the values that I got, x1 to xn, are going to be independent. So there's one next step here. We might remember that the sample is x1 to xn. So the last step here is this is equal to 1 over ps, sum or integral of this times the product, because of the independence given the parameter of the probability of x equal xi, given the parameter, times this density, the prior. And now this is basically your probability of getting this new value, given what you've seen. And the next thing is to make it concrete, inserting the right distributions that, according to your generative model assumptions, and you can actually estimate it. So that's how you do Bayesian inference.